This video could either be titled, "How fast does the Earth need to spin to make everything weightless?" or "How fast does a satellite need to orbit to stay in orbit?" Either way, it's the same formulas. It's just plug and chug. I remember doing this during my first or second year of physics, and so it's pretty easy stuff because you just got the formulas and you just plug in the numbers. I'm very used to things changing on the internet when I look them up, because when I look up anything one day, sometimes I can almost guarantee when I go back the next day, I can't find it. So I remember doing this in physics class, and the formula was really easy because it's just the formula for centrifugal force or centrifugal force. But that formula frequently disappears on Google, and so I happened to get it written down before it disappeared, and so this is what I'm using. All you do for the centrifugal force, back when I was in college, everybody called it centrifugal force, but whatever. It's just mass omega squared times radius. So the heavier something is, or the larger the radius, or the faster the rotational velocity, then the more force it'll feel. The omega will be just change in angle over change in time, and it's given as radians per second. So typically you'll need to convert that to degrees per second for most people to be able to understand that. The other formula is just mass times acceleration equals force. Since we have force here and here, just set these two equations equal to each other. Since we're dealing with the mass of something that's spinning here and here, the masses can cancel out on both sides. We're just left with acceleration. So I'll use the acceleration of gravity for 9.8 meters per second squared. Divide that by the Earth's radius and to get the angular velocity, but you have to take the square root. So you get this in radians per second. Next up, I convert the radians into degrees. 180 degrees equals pi radians. So now we have 0.071 degrees per second. I'm going to convert that into degrees per hour. So you just multiply by 60 squared, but there's the conversions. Seconds cancel out, minutes cancel out. You're left with 256 degrees per hour. So that's how fast, if the Earth is spinning 256 degrees every hour, then everything will be weightless. So let's find out how many hours it'll take for one full rotation of 360 degrees. Just set up the equation like this. It's 1.4 hours per day. So if the Earth is spinning that fast, then everything on it will be weightless. But that also means the Earth will flatten out into a big radioactive disk of dirt and debris. I like to do problems as many ways as possible to make sure I fully understand it, and to just as a way to check my work to make sure I didn't make any mistakes. So we can find the acceleration of gravity here as a different way to do this. Acceleration of gravity is your gravitational constant times the mass of whatever it is that we're talking about, such as the Earth, over radius squared, which will be radius of the Earth. Set this up equal to omega squared r. So instead of acceleration equals omega squared r, we'll have this equal omega squared r, because this is our gravity acceleration. That's not a very good 2 there. There. Okay, so bring your r down to here, and you're going to get r cubed equals this. Solve for omega squared right here, and you'll get 0.00124 radians per second, which is what I got over here. And if you want to set this up for an orbiting satellite, such as the ISS, you'll need to figure out the new acceleration, because let's see here. Acceleration won't be 9.8 meters per second squared for the ISS, because it's a little farther out in space. So you recalculate, but instead of the radius of the Earth, you'll use the radius of the Earth plus the altitude of the ISS. It'll give you a new acceleration, and then you can find out that you'll actually get the same number for the velocity of the International Space Station. So that is one way you can check your work. That's pretty neat, actually. You go through and plug in the numbers again, and you can find out exactly why the ISS travels at the velocity that it does. And it's also a great way to check your work. I was wondering if I was doing this right, because every time I looked up the centrifugal force formula on Google, I kept getting different answers, and then most of the time, or sometimes it would just disappear. And they would talk about torque and inertia, and anyways, the information was gone. But like I said, I'm used to that. So that's why I get these formulas written down before they disappear again, and I'm able to come up with this and then check it against the ISS velocity to make sure it's correct. So yeah, it was kind of fun.